I define a matrix, if I have the nodes, then you will see the first one. Okay, let's define this matrix. It's I define a matrix A, which is 2 0 1 1 3 1 is the matrix in the first example, in the first video. Is a 3 by 2 matrix. I also read it by row. So let's see A. This is the A matrix. It's a 3 by 2 matrix. Then from a library mass, I require this library, and I use the generalized inverse of A, and here is the generalized inverse. If I can get another generalized inverse also. Now let's check whether it's exactly a generalized inverse. Remember, we will say this is generalized inverse. Let me snip it just to write very quickly. We will say it's generalized inverse if let me go with this color. A is generalized. This A inv A1 is generalized inverse if A multiply inv A1 multiply A is equal to A. So if it happens, then I will say inv A1 is the generalized inverse of A. And now let's go back to our code. I define a container result, and I say if they are all equal. So we have two matrices. This matrix obtains from the multiplication of matrices A, inv A1 and A, and another matrix which is equal to R A. And if they are equal to each other, then we say okay, this inv A1 is generalized inverse. So let's define this container result and print it. It's true false, and you see the result is true, and it shows that okay, the inv A1 is the generalized inverse of A. Now let's go with the more pairs. Here you need to install this pragma package. Let me install this pragma package here, and it goes with the cran first. Okay, it's successfully unpacked. Then I require the library. It says that I need another version of R, but it's okay, we still can work with it. Okay, the function here is pinv. Instead of ginv, we write it pinv, and it's Penrose inverse. So usually instead of more, not necessarily usually, you know, sometimes instead of more Penrose they call Penrose, but it's okay. It is what we want. It's the Moore Penrose inverse, and we find the Moore Penrose inverse here. If you compare the Moore Penrose inverse, which is a unique generalized inverse, with the generalized inverse obtained from G inverse, you will see that both of them are the same. So if you remember from one of the videos, I think the first video I said sometimes it's the generalized inverse will give you one solution, but you can have or a matrix can have infinite generalized inverses. And it's just a fun example of linear regression modeling. Remember, in linear regression model we say it's common to write this notation: y is equal to x beta. So I define a matrix X, and then I define a matrix X. This is X, and let's see what X is. It's a 3 by 4 matrix. Then I apply the summation row-wise and put it in Y, and I find the generalized inverse of X and multiply by Y. We expect to get beta, and if this is the beta and we post multiply by X, then the result must be equal to Y. So this is Y, and let's see what Y is. So Y is column vector 32, 26, 20. So we expect using the Penrose inverse or more Penrose inverse of X multiplied by Y gives beta, because here according to this equation you can easily find beta. And then if I post multiply beta by x, then I expect to get y. Now let's see whether it works. Here it is beta. We can also see what beta is. Let me type beta to see what we get as beta. Okay, this is the 4 by 1 vector of coefficients. Now I multiply these two, and if you compare, you will see, okay, this is y. We have 32, 26, 20 here, and this column vector which shows y. So the Moore-Penrose inverse, which is a unique inverse, works. And I hope this our example helps you to find generalized inverses or the unique generalized inverse, which is Penrose inverse, for any matrix easily. And it's not needed indeed to compute the generalized inverse by hand.